I'm going to move on to another application of complex numbers in computer science. So in the last one, quaternions, we saw that quaternions, they weren't directly a use of complex numbers, but the formalism, I would argue, could not have been constructed without the existence of the theory of complex numbers. So it's a rather indirect application. The method I'm going to be talking about in this lecture is a much more direct use of complex number theory. And in particular, it involves a technique called the Fourier transform. And its use in computer science is of importance in how the Fourier transform is applied to develop algorithms for carrying out arithmetic processes. So to start off with, what is this object? What is the Fourier transform? Well, in simple terms, it's just an operation that maps between vectors of complex numbers. So it will take one vector of complex values and it will return another vector of complex values. So in other words, an object like this. We have the operator itself. It takes as input a vector of complex values. It returns another vector of complex values of the same order. And I'd like to note this notation here. We have this double-headed arrow. So what this is indicating is this is a two-way process. We can take a vector, return another vector, but we can recover our original structure in a moderately straightforward way. I'll talk about that a bit later. Where the Fourier transform is used, well, one of the main applications area is in electronics. What it provides is a useful method between these notions in signal processing, which are called the spatial domain and the frequency domain of a given signal. So, for example, the height of a wave and the frequency of that wave. So what this allows us to do in electronics and signal processing applications is if we apply the Fourier transform to the vector describing, say, a particular wave, and we get this as an output, we can process the output in a certain way to try and reduce noise or to try and reduce distortion in the signal, and then we can map back to get an actual signal which we can replay. So sometimes it's easier to carry out processes in one domain to reduce noise or to reduce distortion than it is in another domain. In computer science, however, it is also one technique for carrying out what is called image compression. In a particular form called the discrete form of the Fourier transform, it's the basis for what is currently the fastest known method for multiplying two integers together. So this is a technique called the Schrödinger-Strasse method, which is roughly 50 years old. So what's a formal definition of this object which I'm calling the Fourier transform? So we're given a complex vector, something like this. For reasons which I hope will become clear, we're going to start indexing the components in that vector from 0, not from 1 as we've been doing so far. So the indices of this complex vector go from 0 to 1 up to n minus 1 if it's a vector of, if it's an n vector. The Fourier transform of that vector, it's another n vector. This time we're going to use, instead of x, we're going to use y to denote that vector. So we take a vector of complex numbers and we're going to return a vector of complex numbers. And the way that vector is defined, the individual components, are by this rather daunting looking sum. That sum is actually quite a simple object. It uses a structure which we met already in this part of the module. So if I write, instead of this exponential term here, if I use this notation omega sub k as a shorthand for that, then this summation can be simply written as just this object here. Okay, so what's going on? We take the sum over all the individual components. We take the component of our input vector, we multiply it by this object raised to the power t, and that gives us the tth component of our output vector. There are a number of important aspects of the Fourier transform if we look at that process in more detail. The first one, I mentioned we'd seen this object in the summation earlier in this part of the module. And we have, because this object omega sub k, this is what we called a primitive nth root of unity. In other words, if we take this, if we raise it to the power n, then we get the outcome 1. And we can describe the entire computation not in terms of using sums, but as a matrix vector product. This, again, perhaps rather daunting matrix looking product. So here's our input vector, here's the matrix we use, here's our output vector. Let's look at this matrix in more detail. Suppose we go down the rows of this matrix. Then in the first row, every single one of the primitive roots of unity are raised to the same power, to the power 0. And the primitive root of unity here, this is the first primitive root of unity that we're going to use. And then, so these go up in ascending order. We have the first, the second, and so on up to the last primitive root of unity. But they're all raised to the same power. The same if we go down to the second row. We have the primitive roots of unity going up in increasing order, and this time we're raising them to the power 1. So that's all the way through to the last row, the primitive roots of unity going up in increasing order of index, but all of them are raised to the same power. So that's the rows. What about the columns? Well, in the columns, in the first column, we use the same primitive root of unity, the first one, and the power we raise that to, those go up. So we go to 0 to 1 up to n minus 1. In the second row, we have the same thing. We have the primitive root of unity corresponding to the index 1, and we raise that in increasing powers from 0 to 1 to n minus 1. And that's all the way through to the last column. We have our last primitive root of unity. In the first row, we raise it to the power 0. In the second row, we raise it to the power 1, all the way through down to the last row. So what the notation I'll use, again, this is rather cumbersome to write in general. So we'll introduce this shorthand to describe that particular matrix. And we have a number of useful properties of the Fourier transform. I'm going to mention some of them on this slide. One very important property, which I hinted at when I introduced the definition, is it's very easy to invert. So if we're given some n vector, some complex n vector, and we want to find the complex n vector which would produce that when we applied the Fourier transform to it, then we get that just by applying the Fourier transform to our output vector and dividing it by the number of components in the vector. The Fourier transform defines a linear transformation, the subject we met earlier when we were looking at graphical effects. So if we apply the Fourier transform to the result of multiplying a vector by a constant and adding another vector, then that's exactly the same as applying the Fourier transform to our first vector, multiplying by our constant, and adding the outcome of applying the Fourier transform to our second vector. It has what is called a convolution property. I'm not going to go into details about what that means. If you're interested, I refer you to those pages of the textbook. The convolution property, the reason why I mention that is that's the key to implementing a fast multiplication algorithm. So here, in that particular algorithm, we don't work with complex numbers. What we work with are integer arithmetic modulo some particular value. Now in that structure, we have an analog of a principal root of unity. I'm not going to discuss that in detail. That's also described in the textbook. Okay, so fast multiplication. How do we go about doing that? Well, you may be thinking, why do we need better multiplication algorithms? We learned how to do multiplication probably in primary school. It's a very straightforward algorithm, and perhaps it seems like there isn't much room to improve on it. What we do in that algorithm, we take two n-digit numbers, we take each of the digits in one, we multiply it by each of the digits in the other, and we add a collection of outcomes up. If we count the number of basic operations that process uses, it turns out to be roughly the square of the number of digits in our numbers. Now, I imagine at this stage you've already met the notion of recursive algorithms in Professor Wong's course. So maybe we can do better by trying to find a recursive algorithm. Perhaps we can take our numbers and divide them into the most significant parts of the number, the least significant part of the number, the most significant section of the other number, and the least significant section of the number. And by using recursion, in effect what we're doing is implementing this multiplication in terms of multiplying this by this, this by this, this by this, and this by this. Now, if we implement that recursive process in a naive fashion, what happens? Well, what happens is we don't do any better. The naive recursive algorithm takes about square of the length of the numbers in exactly the same way as this traditional school method does. So here's something really quite surprising. 1962, roughly 60 odd years ago, Soviet computer science, a chap called Anatoly Karatsuba, he found a way of implementing the recursive algorithm, but not in a naive style, in a way that actually resulted in a better, in a faster algorithm. So what does Karatsuba's algorithm do? Well, there's a diagram of it there. Let me talk through this. We take our two numbers, x and y. We divide those up into two equal length parts, exactly as we did when we were trying to find a better recursive algorithm in the first place. So the first thing we do, we multiply this part by this part, and this gives us this term here. Now we're going to need that term, so That makes sense. We then take this term and we multiply it by this term, and that gives us this outcome. And again, we're going to need that term, so that's a sensible operation. We do that in the naive we make those computations in the naive recursive algorithm. And then we do something in Karatsuba's algorithm which is quite strange looking. We take these two components and we add them. We take these two components and we add those. And then we take this object and we multiply them together. Now that looks like a rather strange thing to do. In fact, this computation is the key to the whole algorithm. What happens? We take this object and we subtract from it this object that we've already computed and this object that we've already computed. And when we do that, we get the two terms that we were missing from the recursive algorithm. So when we put everything together in Karatsuba's algorithm, what's happening? The naive recursive method, we use 4 recursive calls to compute the 4 subproducts. This, and this. Now, even though those are only half the number of digits of our original input numbers, the fact that we're making 4 recursive calls, this means the overall number of steps that we take isn't any better. In Karatsuba's method, we don't use 4 recursive calls. We use 3 recursive calls, and we compute these 3 subproducts as multiplications. The term that we need, these 2 terms in the middle here, that is just the result of our seemingly redundant multiplication, this one, and we subtract from it the 2 necessary terms, this one here and this one here. Now, we're taking some extra addition steps, but that doesn't really matter. Addition is a cheap operation. The fact that we save 1 recursive call, the outcome is we only need much less than n squared operations. Okay? Why should we stop there? Karatsuba's algorithm, we split a number into 2 parts. Instead of 4, we use 3 recursive calls. And we could try the same thing. If we split into 3 parts, we would have 9 obvious multiplications needed, but we might be able to find some way of doing them in 5. If we split into 4 parts, we would have 16 obvious multiplications, but maybe we can find some way of doing them in 7, and so on. The problem with that approach is it very quickly becomes quite onerous, it becomes difficult, first of all, to find clever ways of combining the subterms, and secondly, we end up using a significant amount of additional steps, these extra addition steps. So very quickly this ceases to be an effective method. The other approach we could take is to take our initial numbers and divide them up into sections whose length depends on the number itself. And this is what the Schrödinger-Strassen algorithm does. It takes our n-digit number and divides it up into roughly the square root of n sections, each of those sections having the square root of n digits. And the convolution property in the Fourier transform that I mentioned, this results when we carry out this method, this results in an algorithm which takes roughly n multiplied by the logarithm of n steps. So this is a huge saving on n squared. So let me just summarize what we've seen here. The Fourier transform has a very powerful range of applications in electronics and in signal processing. The basis of the Fourier transform is this complex analysis notion that we met earlier, called the primitive root of unity. In computer science, one of the most important applications is in fast algorithms for carrying out multiplication. There are other uses, one of which is in image compression, that's described in the textbook. We also have, again I described those in the textbook, a number of fast algorithms to compute the Fourier transform itself. In the final section of our look at complex numbers, I'm going to look at quite a different application of complex analysis in computer science. And this is to the area of artificial intelligence and computer creativity. So that's what we're going to look at in the next lecture.